In this section, we're going to use a method of comparison to determine whether series converge or diverge. And so if we look at, when we talk about a comparison, we mean, we want to compare something that we know to something that looks similar, but we don't really know what's happening with this. So if we look at this, we talked about this in section 2, and it's a geometric series, and that's the same as saying 1/2 to the n power. And so we know that this is a converging series. And then when we come here, we look at this and we say, well, it's got a lot of characteristics of a geometric series, but the numerator is different. So how does it compare? And so we're going to have a method that we're going to be able to use that is going to allow us to determine whether we can just consider this as something that looks just like this. Likewise, if we look at this is a P series, and we know that from section 3 that P series converge when this is greater than 1. So we know that this is a convergent series. This looks similar, but the denominator is slightly different. How does this compare to that? And likewise, in section 3, we know we can integrate this with a u sub. And so if we can integrate this with the u sub, and then we look at this, and these should have, we should really have some series notation here. This is slightly different. We have an n squared in the numerator, so u sub won't work anymore. So how does this compare to something that we know how to determine convergence or divergence on? So really what we do then is we look at a term-by-term comparison. So in other words, we take a look at, here's the first series, here's the second series. So these are terms in one of the series. And these are terms in the other series. And then we just take a look at, we do a term-by-term comparison. So this one, if we look at this inequality, we're saying a sub n is bigger than 0, but is less than or equal to b sub n. So we look at a sub n as the littler of the two, and b sub n is the larger, the bigger of the two. And so if we look at that comparison and we just kind of draw a quick sketch here, so we have a sub n, which is the littler of the two, so it might look something like this. And b sub n, which is the bigger of the two, so it might look something like this. So if we look at that, then we can say, well, if we take b sub n here, those are the terms in the B series, and if we look at a sub n here, and let me just copy that before I talk about it, because I want to use that for the next picture as well. So if we look at this here, then what we're saying is, for this first statement here, if b sub n converges, so if we know that this is convergent, what we're saying then, if this is convergent, then all of the convergent series lie underneath here. So if we look at that, then all of these series are also convergent. And the reason being is because if B sub n is convergent and we take a look at a term by term comparison, then all of the A sub n terms, which would be lying right here on the red line, or on the red curve, all the A sub n terms, term by term, are smaller. So if B sub n goes to a finite value, if we know that the series B sub n goes to some finite value, and A sub n is smaller, then A sub n must also go to a finite value that's somewhat smaller than B sub n. So if B sub n converges, then A sub n must converge. Okay, and then we can apply the reverse logic to it also. If A sub n diverges, so here's A sub n, and when we talk about diverging, we're talking about A sub n going to infinity, you know, the series going to infinity. And so when we talk about diverging, we're talking about looking above that function and saying, well, if A sub n goes to infinity, then all of these series that are located out here also diverge. And so what we're looking at then is, you know, if we look at A sub n term by term, so here's A sub n term by term, B sub n term by term is going to be larger for each and every term. And if B sub n is larger for each and every term, and A sub n already goes to infinity, then B sub n must go to infinity at a faster rate. So B sub n must also diverge. So if A sub n diverges, if the little one diverges, then the big one's going to also diverge. So we kind of sum this up that, looking back up here, if B sub n, if the big one converges, then the little one, by comparison, also converges. And if the little one diverges, then the big one also diverges. So if the little one diverges, the big one also diverges. And I think I just explained this up here with those sketches. So we won't really need this picture at all. So when we use the direct comparison, what we're saying is we're just really taking what we have and rewriting it to make it look simpler and to make it fit into something we already know. So for instance, we take a look at the series here and we say, gee, it would be awfully nice if this minus 1 weren't here, because if the minus 1 weren't here, then we would have something that looks like 1 over the square root of n. And 1 over the square root of n is just, can be rewritten as 1 over n to the 1/2 power. So we know we have a p-series. So the first thing to establish is, what am I going to compare this to? And I'm going to compare this to this function. Next step, so if we kind of write down the steps here, what are you going to compare it to? Compare series 2. So that's the first step. The next step then would be to determine which series is A sub n and which is B sub n. So in other words, determine which one's going to be the little one and which one's going to be the big one. Mathematically speaking, which one's little and which one's big comparatively. So if we look at this, term by term, and if it's tough to determine which one's little and which one's big, you can really just graph these as functions on your calculator, and take a look at which one's smaller term by term. But if we look at algebraically, if we look at the comparison of the two, this is the denominator, and this denominator is smaller than this denominator. So the denominator is small. And if the denominator is a littler number, then the whole series is going to be bigger. Than what we're comparing it to. So that being the case, then this is going to be your a sub n, and this is going to be your b sub n. And so as it is, then we really can only use the direct comparison in this situation to determine divergence. So we better hope that this diverges. So at this point we want to then, there we go. At this point we want to test the comparison. Okay, so at this point we want to say, well, this series here, p is equal to a half, and that's less than 1. So we know that n to the 1/2 diverges by p series test. Okay, and so b sub n is out here somewhere. So therefore, 3 dots mean therefore. Therefore, this series is bigger and must also diverge by p-series test, by direct comparison test. And I usually write direct comparison DCT, direct comparison test. So we had a divergent series that we knew, and we also showed mathematically that that the series we're trying to find information about is bigger term by term, so it must also diverge. If this ended up converging, we'd have a problem, because if this converges, then we don't really know what would happen to b sub n, since b sub n is bigger. And in that case, we'd have to just choose a different test, and by the end of this chapter, you'll have a ton of tests to choose from. When we look at this series here, we would kind of look at this and say, wow, this series would be a lot simpler if the 5 weren't there. So we're going to look at 3 over n, or 3 to the n, over 4 to the n. And that also can be rewritten as 3 over 4 to the n. And once we rewrite it in this form, we can see that it pretty much falls into the geometric series category. And so if you remember, we're looking for that r value. Our r value is whatever's raised to a power, and 3/4 is raised to the power. And that's less than 1. And we know the criteria is that the absolute value of r has to be less than 1. So we have to trap r between -1 and +1, which we have done. So we know that this series converges by geometric series test. So this is the series 3 over 4 to the n. We know it converges. Hopefully this is smaller. We'll get to that in a second. But for right now, since we know this series converges, we're using the geometric series test for convergence, or we're using the direct comparison test to determine convergence. And so if we again look at this, we see that the denominator here. So if we talk about the denominator, 4 to the n plus 5 is bigger than 4 to the n, which means 3 to the n over 4 to the n plus 5, and 3 to the n over 4 to the n. Okay, if the denominator is bigger, then when we look at the whole fraction, this whole fraction is smaller. So we know then that this series is smaller than this series. So that being the case, then this series is our a sub n, and this series here is our b sub n. So we know this is our b sub n, and we know our a sub n series then falls term for term right here. Oops, should be a 3. There we go, our a sub n, 3 to the n over 4n plus 5 should be right there. And so since our original series is smaller, then we can conclude that the series being smaller also converges. Because of the direct comparison tests. So if you notice in this, I kind of modified the steps a little bit, but I provided a kind of summary of an algebraic proof here. I provided some algebraic proof to say that this is definitely smaller than something that already converges, which allows me then to state this conclusion here.